Okay, we left off in class working on this example, which was the unloading sand on a scale. And we know we're working on the endeavor. All this week we're working on this problem. There's question in calculus of, you know how fast something is changing at every moment. You want to know how much of it you have at every moment. And so we've seen that generally this means we're going to start with an exact rate of change function. And that was this red curve. We said we can't make any progress in getting towards accumulation or how much we have without having constant rate of change, because we're going to use dy equals mdx. So we take that exact rate of change and we form what we call a pretend rate of change function. That's this blue one. So here's a new function r, which is trying to pretend to be like our exact rate, but it's doing so with constant rates. So with constant rates, we can use dy equals mdx, and those dy's are little changes in the quantity, and so that helps us, those dy's allow us to build accumulation. So when we take this pretend rate of change or approximate rate of change function, that results in this purple or pink graph here. That's our approximate accumulation. And we see it's doing a generally decent job of mimicking what we know or expect to be the exact accumulation. And so where we left off in class then was we found A of 0.8. So this is the last screen we had in class on Friday, and A of 0.8, it represents one value. So A of 0.8 represents one value of this A function. So we were just trying to get a feel for how is this A function generated. And so we looked at just one value, A of 0.8, which would be this point, the ordered pair 0.8 and A of 0.8, which looks like it's pretty close to 100 pounds. And that was, what we did was we got the accumulation from the first interval plus the accumulation from the second interval, again, m dx, or m delta x, plus m delta x for the second interval. And then to get to 0.8, we actually don't go through a whole interval. We only go through 0.2 seconds here to get to 0.8. So then we have m dx again, but now that change in x is 0.2. So when we add those three up, we get the net accumulation of weight in the first 0.8 seconds. And again, that calculation is kind of representative of one point of all of these points on this approximate accumulation graph. So if we thought about we know that the next thing we want to do is look at more smaller intervals to make this pretend rate function more accurate, and then the approximate accumulation function to be more accurate. And so that would, as we take more and more smaller intervals, then we're looking at more and more of these m delta x added together. So because they're all m delta x, let's just write it once and use summation notation, which represents adding together this m, which is rate of change, times delta x. And the summation means add a bunch of those up. Maybe it's 10, maybe it's 20, maybe it's 100. However, so one for each one of the completed intervals. And so this means the sigma means sum up changes in y calculated by m delta x. And then we know, well, I was going to have that one current interval where the change in x will be less than delta x, something depending on where x falls in the current interval. So we call that amount dx. So this is basically how we come up with the A function. So we can write A has this general form again, and that's looking at this pink function. I'm going to rewrite that here. So that's our approximate net accumulation function, and there it is again. And so then what happens when we make delta x really, really small? Well, the smaller and smaller we make delta x, the more accurate our pretend rate function is, and the more accurate our pretend accumulation function is, and the more and more intervals we have. And so we talked about, to get the exact accumulation, we just need to make the intervals small enough so that we can't tell the difference between approximate and exact. So we have new notation for that, and it's notation that you've seen before, but maybe some of you have known what this meant or didn't. But to get exact net accumulation now, in other words, letting delta x become very small and taking many, many intervals so that we can't tell the difference between the blue graph and the red graph, and also can't tell the difference between this purple graph and this black graph, that is where integral comes in. Exact net accumulation is this integral function. Okay, so before we had Greek sigma, meaning sum up a bunch of changes in our quantity. Now we have German S, which also stands for sum. We're summing up a bunch of also changes. So this is still representative of m delta x, but just for a very, very, very small, tiny interval. And so the succession of constant rates then becomes like the continuous rate function because the intervals are so small. So we really have this parallel situation now, this kind of more succinct notation that means the same thing as this. Sum up a bunch of changes in the quantity according to the rate of change, starting at a starting point, a starting value of x, up until the current value of x. And that makes an exact accumulation function. So really this right here is kind of like it's kind of the conclusion of this whole week. It's the answer to this question. You know how fast something is changing at every moment, and you want to know how much of it you have at every moment. So given how fast something is changing at every moment, the rate, we know we're going to use m dx to get little changes in accumulation, and then by accumulating all those or summing all those up starting from a certain x value up to x, we get what? We get how much we have at every moment, or in other words, we get the net accumulation, and this time it's exact because we're considering very, very small intervals. So this function right here is the answer to this endeavor or this problem that we set out on day one of class, and the notation kind of encompasses this whole journey we've been taking in these 3 days. Once again, you know how fast something is changing every moment. You want to know how much you have at every moment. How much you have at every moment is this integral expression, the sum of many changes in the quantity m times change in x. Okay, so what if to start with there was p 100 pounds of sand on the scale already? Then what would the total accumulation be? What would the W function be? And so the W function would be, well, it would be the p 100 pounds of sand plus the amount of change at x seconds. So to get the total accumulation, we would start with the p 100 pounds of sand, and then add the amount of change that you get in the first x seconds, and that's now the total weight after x seconds. So it's like we talked about, it's a very easy step to get from net accumulation to total accumulation. You're just going to add the starting value. By adding the starting value, at x seconds, you're going to always have the weight on the scale. So it's going to be the starting amount plus the amount of change. So we have arrived here. These are our functions that give us how much we have at every moment, given in the beginning how fast the quantity was changing at every moment, or given r sub w, the red curve down here, the r sub w function. Okay, so whenever you see an integral, we want to think of that integral as this sum of many bits of change due to completed intervals plus a little more change due to the current interval, but with a small enough value of delta x so that values of a are indistinguishable from the exact accumulation. And when your delta x is small enough so that things are indistinguishable, then really the current interval is kind of absorbed into the model. There's really no difference anymore because the interval width is so small that this really doesn't matter anymore. So how are they the same? So for each of these items, 1, 2, 3, and 4, we see it expressed in both notations, and part of your homework for Wednesday will be to explain how you see each one of these in each notation. So the first one is, you know how fast something is changing. Where do you see that in this expression? You know how fast something is changing. Where do you see that in this expression? Okay, because again, where in each of these do you see we want to know how much of it we have? Where in each of these do you see which is found by summing up, the idea of sum? And where in each of these do you see many bits of change? In other words, dy. Where in each of these do you see dy? Okay, and then you can ask what's the independent variable of each of these functions? What does it mean? And what's the dependent variable of each function? And what does it mean? Okay, so let's practice with some expressions here. So when you see an expression like this, which should be a familiar expression from, say, Calc 1, we should see it in a new perspective now. We want to think of this, whenever you see an integral function like this, you want to think of it as some net accumulation function. So to describe that expression, we might say this. Here's one way to describe that expression. This is the exact accumulation of changes in some quantity f of x due to its changing rate of the square root of x at every moment t from 3 to x. So t is actually a symbol we're using for values of x that vary from 3 to as far as we're accumulating. So this is one way to describe that expression. So here are two more expressions, and you could pause the video and try in your own words to explain what these expressions mean. See if you can do it in your own words rather than just kind of regurgitating this explanation that I have. Okay, so again, thinking about these integral functions, we want to think of them always as a net accumulation function. So here's another way to describe a net accumulation function. I wrote this is the exact net change in a function, say f, as u changes from negative 4.8 to x if the rate of change of f is the sine function. So that's just another variation on explaining what this expression means. So now this next one, you see it's 0 to 12 instead of 0 to x. You still want to think of it as a net accumulation function, but now just one particular value of that function. So in other words, a sub f of 12. So I described it this way. This is the exact net change in some quantity having a rate of change of x squared minus 7 as x changes from 0 to 12. So this expression is not a function, but is actually a value. It is an amount of accumulation, or a net change. Whereas these ones above, these first two, were actual accumulation functions. They were functions of this x value, the current x value that we were accumulating to. Okay, so here's a scenario that you want to, will be another homework question. It says when Katie unties a partially filled balloon and inflates it with more air, the volume increases at a rate at 2 over x plus 1 inches cubed per second, where x is the time elapsed in seconds since Katie began inflating the balloon. The volume of air in the balloon is 18 inches cubed at x equals 3 seconds. Write a function for v of x, the volume of the air in the balloon at x seconds. For what domain of x is your function valid? So this is a good application problem. You're not doing there's no algebraic solving here. There's no kind of computation to do. This is just writing the function. For instance, like the ones above on this screen. So you're taking the information given and writing out the function v. In other words, v of x equals what? Okay, so be sure to read Blackboard carefully so you know exactly what's due for homework, and then take advantage of office hours on Tuesday. Come in and see us, get all your questions answered from this homework, and then we'll take it from here on Wednesday in lecture.